Hello and welcome back to another installment of NatLab video. In this video, we will take a look at a quick way to measure zeta potential using electrophoretic light scattering. Most colloidal particles have an electrical charge in liquids. Let's take a look at an example. The surface charge of the particle is negative. The layer of positively charged particles around the negatively charged surface is named the Stern layer. Then, a diffuse layer composed of ions of opposite polarities encapsulates the first. These ions are free to move due to the influence of electric attraction and thermal motion rather than being firmly anchored. Combined, these make the electrical double layer. These ions are overall a neutral charge. The edge of this double layer is called the slipping plane. Zeta potential can be described as the electric potential difference between the slipping plane and a point in the dispersion fluid that surrounds the particle. The direction of electroosmotic flow depends on the electric field applied. Particles move towards the electrode with the opposite charge. Electroosmotic flow may also be induced from the surface charges of the cell wall. When measuring the zeta potential using electrophoretic light scattering, both the electroosmotic flow and the particle true mobility must be accounted for. Small frequency shifts are measured from the differences between the reference light and scattered light. Subsequently, the electrophoretic velocity can be found from the frequency shifts. After the electrophoretic mobility is calculated, the zeta potential can be found. In the following equation describing the frequency shift, the scattered light is related to the mobility of particles, mu. N is the refractive index of a medium, theta is the scattering angle, and lambda is the wavelength of incident light. We can now use this Minkowski equation to obtain the zeta potential given the solvent viscosity, mobility, and dielectric constants. Higher zeta potential numbers will indicate stability, while a lower zeta potential number will indicate coagulation or flocculation. 30 millivolts can be considered the stable and unstable dividing line. Let's take a look at an example. The zeta potential value in this result shows a value of negative 58.4. From our table, 58.4 is considered stable. Units are given in millivolts, while for mobility it is centimeters squared per volt second. Different diluents can affect particle migration or sample consistency, so it is essential to use a diluent best suited for the sample. In this case, distilled water is used. The blue line is the raw data, the red curves indicate the fit, and box 1 indicates a Lorentzian peak. When analyzing zeta potential, pH can influence the result. Some samples will have an isoelectric pH, the pH at which there is no net charge. In this example, the isoelectric point lies at a pH of 5.69. That's all for this installment of Ebatco Lab TV. We hope you enjoyed and will visit us again. Keep an eye out for more videos covering diverse topics from our lab. If you have any questions about either the methods or the instrument you saw here today, please don't hesitate to give us a call or shoot us an email. Our contact info can be found on our website. And as always, if you are interested in nanoscale material and advanced surface characterization lab services or consultation, please contact us. We'd love to hear from you.